I'm assuming everybody can hear me, and if you cannot hear me, let's let me know in the chat box. People hear me? You haven't said anything.
We got it.
Thumbs up, good. Okay, so one more lecture after today. Sadly, I know you're depressed about that, but all good things must come to an end. No one wrote me about changing the times of the review session on Monday, so expect after class I will post an announcement as well as the Zoom meeting schedule for probably Monday 9:30 to 11:30. That's probably the window. And remember, you can always send me an email note with questions. You can schedule your own Zoom meeting if you like. Just remember, the closer and closer to the exam, everybody wants a piece of my time, and I just don't sit in my office all day doing nothing. I have a lot of other things to do. So the closer and closer to the exam, my time gets a little more precious, and I may not be able to squeeze you in. So if you have questions, you should really start studying for the exam now, and get questions to me as soon as possible. So today we're going to switch directions a little bit. We've been focusing on flow and closed conduits. And now we're going to apply what we know about fluid mechanics and look at the case of what we term open channel flow. So, if we're looking at how we can describe flow in open channels, the first question is, what is an open channel? And the most important distinguishing characteristic for an open channel that makes it different from a closed conduit is there is a free surface. That free surface is described by an elevation, the water surface elevation, and in open channels, that water surface elevation, because it's a free surface, is the hydraulic grade line. For closed conduits, the hydraulic grade line could be anywhere, above the pipe, below the pipe. It could possibly if it be at the top of the pipe. But this is the distinguishing characteristic that makes this an open channel. You can have open channel flow with a free surface in a closed conduit, for example, a sewer. So you might have a 10-foot diameter sewer, but the water depth may only be 1 foot deep. So that's a free surface in that closed conduit, so to speak. So just recognize this is the defining distinction. For open channel flow, gravity is the dominant driving force. However, you should know that water can flow uphill, and you see this happen every day, you just don't think about it. Water, or in the general case, fluids, flow in the direction of decreasing energy. That's what's important. So somehow that very last bullet, fluids moving in the direction of decreasing energy, somehow conventionally or colloquially transferred to water flows downhill. Water does flow uphill. And then generally in open channel flow, what we have is fluid statics occurring, and I'll describe that a little bit more in future slides. So this whole course has revolved around the 3 laws of fluid mechanics: continuity, the energy equation, and the momentum equation. These are the same 3 equations we apply to open channel flow systems. For example, the hydraulic jump and what you had earlier as a lab, the sluice gate, were all forms of open channel flow in which we applied momentum and continuity and energy. So just as a waltz down memory lane, remember when we talked about flat plates? We had flow over the flat plate, the no-slip condition, and ultimately what that led to is a velocity profile. The same thing happens in open channels. Although there's no leading edge to the open channel, just like in a pipe, a closed conduit flow, there's no leading edge, but there is an established velocity profile, and that profile has a boundary layer with characteristics of either being laminar, transitional, or turbulent. Same thing in open channel flow. By and large, with open channel flow, because of the roughness elements on the bed, typically you have turbulent, in some instances you could have transitional boundary layers. Laminar open channel flow is extremely rare. Places where you see it is on the thin veneer of water flowing down a cave wall, or when it rains really hard and you get a thin veneer of water flowing over a parking lot surface or a road surface, that can be laminar flow. And again, the importance of the velocity profile is as you have velocity changing with elevation, that generates a shear stress between the layers. So the velocity gradient, how the velocity changes with elevation away from the bed, is descriptive of shear stress. And remember, what we did was include Newton's law of viscosity and this concept of shear stress. And this is the same thing that's done in open channels. Ultimately, to give us the shear stress anywhere in the fluid, where we care about it most is on the bed of the channel. And we'll talk about that a little bit later. So everything that we talked about before for flat plates and closed conduits is the same thing is happening with open channels. So for open channels, there is an infinite number of cross-sectional geometries you can look at. One class that we will probably use in this course the most is what we call a prismatic cross-section geometry. And that just means that the cross-section has the same shape as you move down the channel. And that shape can be rectangular or square, which is a subset of rectangular, trapezoidal, or other. So again, this figure shows prismatic shapes. And there are many other prismatic shapes. But the essence here is this shape remains constant as you move downstream or upstream of the channel. When a problem says you have a prismatic channel, that's what you have. And very often in design, when we're designing swales or flight control channels, we actually typically build prismatic channels like this. And then obviously you can have an irregular channel. And that is what you find out in the environment for streams and rivers. There is no prismatic aspect to it, although you might approximate the natural system as a rectangular or trapezoid if you're just trying to get a coarse estimate of what's happening. So in open channel flow, here you see a cross-section of a stream, and the flow is going from left to right. And in this cross-section, what we typically design from the lowest part of the channel to the water surface or the free surface. Obviously, you can have any liquid flowing in an open channel. We call that the depth of flow, and that commonly is denoted by Y. Some textbooks will use lowercase d. The cross-sectional wetted perimeter is that portion of the cross-section here in orange that is wetted by the fluid. So that's called capital P, the wetted perimeter. And then the area normal to the velocity vector is the cross-sectional area A. And as we saw when we were talking in closed conduit flow about non-circular cross-sections, the hydraulic radius, either denoted capital R or R sub H, is equal to the area divided by the wetted perimeter. Sometimes in open channel flow, that is referred to as the hydraulic depth. Hydraulic radius is sometimes called hydraulic depth. So again, the shear stress on the bed is where all the frictional resistance comes from, and therefore the energy losses, just like in a pipe. And if we looked at forces along the bed, so for example, if we took a cross-section here along the channel, and we had hydrostatic conditions, so we could calculate the forces, what we would find from this analysis, remember we've got gravity acting down the plane, what we would find from this analysis is that the shear stress on the bed is equal to the specific weight of the fluid times the hydraulic radius. That's actually the shear area over which the shear stress acts, times the slope. And slope is vague right now, so just look at this as slope, and we'll talk about that later, which slope we're talking about. So again, just like in pipes, we can describe a lot of relationships. And curiously, in open channel flows, very, very often we run into this term shear stress on the bed divided by density square root. And that just happens to have the dimensions of velocity linked to the time. And therefore, since it is derived from the shear stress at the bed, it's called the shear velocity. And this term crops up very, very often in many open channel flow situations. And in fact, when you're looking at particle stability or sediment transport, that is rip-wrapping a channel, what particle do you need to put down to keep the particle stable? The shear velocity is often one of the players involved in that calculation. So again, if we look at the shear velocity and the fact that before in a previous slide, we developed that the shear stress on the bed is the specific weight of the fluid times the hydraulic radius times the slope. If we divide gamma by rho, you get the acceleration of gravity. Remember, gamma is equal to rho g. So again, that's another way of calculating the shear velocity. And you'll see this mentioned in your textbook readings. And once we know the shear velocity, just like we did along flat plates or even in pipes, there's a velocity profile that you typically have in open channels. What you're seeing here is in a flat plate, the velocity profile, the turbulent velocity profile on the flat plate. If you recall, I gave you a handout, and it was all about development of the boundary layer. The handout was called Boundary Layer Theory, and this was the turbulent velocity profile for flat plates. The velocity profile in real open channels look very similar to this. Question?
They're asking if S is specific gravity.
No. I think I mentioned it earlier, maybe I did not.
No, you passed it.
Yeah, hold on. I did pass it,
So that was just one slide ahead.
didn't I? What?
That was just one slide ahead of what you were.
Yeah, I know I had it on one slide, and I just want to find that slide. I guess I didn't say it. I thought I had that somewhere. So, I know I talked about it. Oh, it was on gamma RS. There it is. So, capital S is the slope. And I don't think specific gravity is in this talk at all today, but I know we use capital S for specific gravity in the past. I'm trying to use the terminology consistent with your book and consistent with what you see people using when they talk about open channel flow. And again, there's more to talk about in slope. So, energy. For the energy equation, what we needed to do is describe energy losses. And the energy losses are typically built into the energy equation. So when we're talking energy, we're saying that we can draw a path line, and along any path line, we can say that the upstream energy is equal to the downstream energy plus sum of all the losses. And the losses are typically friction and minor. Just as in closed conduits. The friction loss is what's described by the Manning equation, or what is embedded in the Manning equation. So I hold that as a placeholder, we're going to get to it. So you have a handout for today, and the Manning equation is page 2 on that handout. This is the exact same equation. And in this equation, V is the average velocity of the cross section. So V is Q over A. It's an average velocity. K is a units conversion. So this equation is dimensionally consistent. So what you have is hydraulic radius as the units of length to the 2/3 power. Slope is dimensionless. The roughness coefficient, as you see, is dimensionless. And what we have on the velocity is length per time. So on the right-hand side, we have length to the 2/3. And so K is the conversion factor, and it has the dimensions of length to the 1/3 per second, length to the 1/3 per time. You will never see people put the dimensions on K, ever, but it actually does have dimensions. So in metric, in SI, K is 1 meter to the one-third per second. If you convert meters to the one-third to the slope to the one-third, 3.28 feet per meter to the one-third power, you get 1.486. Most people use 1.49 for K. So again, K is dependent on the units you're using, whether you're using the British gravitational system or the international system. And it's the Manning-Rowe reference coefficient. It's dimensionless. We'll talk more about that. And so just like the Hayes and Williams equation in pipes, where the Hayes and Williams roughness coefficient was only a function of the material, similarly, the Manning's roughness coefficient is only a function of the bed roughness, the bed material. Hydraulic radius is area divided by cross-section wetted perimeter, as we just discussed in a previous slide. And S is the slope, and again, more on this later. If it helps you get a physical description of what this means, think of it as the bed slope of the channel for now, but it's a slope. And so the slope, as you know, if it's the bed slope, we'll call that S0, and that's equal to a change in elevation over L. And so typically, if this is the plus X direction, and this is the direction of flow, delta Z would typically indicate that you're decreasing elevation in this sketch in the direction of flow. And so delta Z, or dz dx, L represents dx, should be a negative number. So if this is your stream bed, and this is the x and this is the y direction, that bed slope should be a negative number. However, by convention, a slope like this in open channel flow parlance is just a positive number. When someone says you have a 2% slope, it is decreasing in the direction of flow 2 feet for every 100 feet you go. If you said you had a negative slope, minus 0.02, that's known as an adverse slope. An adverse slope is the fluid flowing uphill in the direction of flow. So a negative slope in the conventional discussion of streams, a negative slope is an adverse slope, where the bed elevation is increasing, going uphill as you get downstream. Obviously, if you look at that Manning equation and you put a negative number in there, you don't get an answer. Also, if the slope, the bed slope were to be 0, you would get a 0 out of that equation. Yet in the fluids lab, when you did all your labs, the bed slope of that flume is 0, and yet you had flow in it. So again, slope is something I'm going to talk about in a future slide. If it makes you feel better to put a physical meaning on it, think of it as the bed slope, but it's actually not. Sometimes we'll just assume it to be the bed slope. So we're going to talk more about the slope later. So for the Manning's N, again, typically where you get Manning's N is from a lookup table. So this is page 3 in the handout I posted for you today. It's also a table from your book. And so typically you will get Manning's N from a lookup table. You can certainly calibrate Manning's N, and that means you would take the equation on the previous slide and solve it for Manning's N, which means everything else you need to measure in the field. So, for example, if you said you had a gravel bed river, straight gravel bed river, Manning's N would be 0.025. And there's much more to this. This is really oversimplifying it. There are entire books and courses on open channel flow. And there are entire books written on just Manning's N. So this is very, very simplified right now for the last 2 lectures of this course. But the Manning equation is what's used for open channel flow calculation. So there's different categories of open channel flow, and this is a figure right from your textbook, right from the handout for today ultimately. You can have laminar or turbulent open channel flow, as I previously identified. Just like in pipe flow, there is laminar or turbulent pipe flow, and we use the Reynolds number to distinguish when we had laminar versus non-laminar pipe flow. For pipe flow, the Reynolds number needed to be less than 2,000 to be laminar. For settling of a sphere, the Reynolds number had to be less than 0.01. So the Reynolds number boundary between laminar and turbulent, laminar in transition and turbulent, that boundary differs depending on the flow scenario. Similarly, for open channel flow, typically you can maintain laminar conditions if you have a Reynolds number less than 500 for open channel flow. You can certainly have open channel flow that's compressible or incompressible. What does that mean? Well, the incompressible fluids are liquids, water, molasses. Compressible fluids would be gases. So you can have gases moving in open channels. For example, and this is actually pretty deadly, in Africa and other places of the world where you have volcanic systems, you can have lakes in the caldera, and those volcanic lakes will be capturing the gases that are also coming out of the earth from the volcano. So, yes?
Sorry, so a couple seconds late, but does the Reynolds number for open channel flow use the average velocity of the Manning equation?
Just like pipe flow. Yes,
Okay.
just like pipe flow. So Lake Nyos in Cameroon, CO2 would collect at the bottom of the lake because it's in a caldera. And remember, a caldera, you have a lake in the bottom and then you have high walls around it. And then irregularly, maybe decadal to every 20 or 30 years, there would be so much CO2 that collected in the bottom of the channel it would basically burst. And this a massive amount of CO2 would then fill up the caldera and flow over the sides. The CO2 is heavier than air. So it would flow down the valleys where everybody lives and asphyxiate everything that lived off oxygen. So you would see mass kills of villagers and all of their animals. But anyway, there are such things as compressible open channel flow. When we were in lab, we talked about what is supercritical and subcritical flow. We typically use the Froude number to describe this, average velocity over the square root of acceleration due. And if the Froude number is less than 1, you have subcritical flow, greater than 1 supercritical flow, equal to 1 critical flow. You can have steady or unsteady open channel flow. So think of steady or unsteady. If you're sitting by a riverbank and you're fishing, steady flow means that the discharge is constant while you're there, which means the water level would be constant if you look at the Manning's equation. So the depth of flow is constant, the discharge is constant, the velocity is constant at that one location. Unsteady flow, think of a dam breaking upstream and this floodway moving downstream, and as you sit there fishing, the water level increases and the discharge is increasing and the velocity is increasing, cross-sectional area is increasing. So what you have is temporally variable variables in this Manning equation. And then you can have what's called uniform, non-uniform, or varied, if it's non-uniform, varied flow. In this case, take a snapshot of the river system. And as you walk along the river system during that snapshot of time, uniform flow is when there is no change in the depth or the cross-sectional geometry as you move along the channel. Non-uniform or varied flow is where as you move along the channel, you actually see changes in the, say, depth of flow or everything else, which is a real stream. You have riffles, shallow, fast-moving water, and pools, deep, slow-moving water. So you can mix and match from this list. You can have turbulent, incompressible, subcritical, unsteady, uniform flow, etc. You can have any one of these. By and large, for this course, we'll talk about steady and either uniform or non-uniform flow. And we'll do some examples so you can see what we're talking about. So this figure is, again, from your handout. And there are different categories of uniform or varied flow. Where the change in the velocity and the depth is very slow, we call that gradually varied flow. And where we have dramatic changes in the velocity in a very, very short distance, or a dramatic change in the depth of flow in a very, very short distance, we call that rapidly varying flow. And why we distinguish between these is because when we have gradually varied flow, we only need to use the continuity in the energy equation. When we have rapidly varied flow, that old litmus test, is there a dramatic change in the velocity vector in a short distance? Where we have rapidly varied flow, we need to use all three equations of fluid mechanics: energy, continuity, and momentum. So again, for this section, we'll be focusing on gradually varied or just uniform flow, steady flow. So for steady uniform flow, again, what steady means is that at one location, the discharge is not changing, which means the velocity is not changing, and then by Manning's equation, the depth of flow, the cross-sectional area, they're all the same, they're staying constant. Uniform flow, again, means that as you move along or downstream the channel, the flow geometry is not changing. The depth of flow, the area, the weathered perimeter, the hydraulic radius, they're all the same. So steady uniform flow means that none of these geometric variables are changing as you move along the stream. That is, when we say y is not equal to y of x, x is when you're moving along the stream, and this basically says that the depth of flow is constant, area constant, P constant. And also for steady uniform flow, the pressure distribution is hydrostatic. And all that means is the pressure at the bottom of the channel is the specific weight of the fluid times y. P is equal to gamma y, something we derived a long time ago here. So this is a graphic depiction of steady uniform flow. And what you see clearly is the bed slope. You can also see the slope of the water surface. And the energy grade line is up here. So remember, the energy grade line is Z plus P over gamma. And remember, if your point is at the bed, the depth of water there is gamma. The depth of water there is y. The pressure there is gamma y. And the P over gamma term in the energy expression is just y. So the water surface elevation is equal to the hydraulic grade line, which is the elevation of the deepest part of the cross-section plus the depth of flow to the free surface. And the energy grade line is always going to be V squared over 2G above the hydraulic grade line, which again is V squared over 2G plus Y plus V. And the energy grade line typically has a slope of SF. And you will see this on another slide, but I'm going to point it out here. For steady, uniform flow, those three slopes are the same. And that's why you can assume the bed slope goes into the Manning equation. And this is what we typically use in design. We'll take the maximum discharge we have to move, and then we'll design a channel, and then we'll put the bed slope in there because for steady uniform flow, it's equal to the slope of the energy grade line. What should always go in the Manning equation is the slope of the energy grade line, SF. The friction slope isn't there. That's what should be in the Manning equation. And in the Manning equation, SF is H sub F over L. Again, the comment I made early on is we use the Manning equation to describe friction losses. And friction losses are built into the friction slope. And if you wanted to just calculate that friction loss, you could isolate the Manning equation for H sub F. But when S sub F, the friction slope, is equal to S0, the bed slope, that just says that H sub F is equal to, that's supposed to be an F, delta Z. Basically, in steady uniform flow, the energy you're gaining by going downhill is consumed by the frictional resistance. So, if we had gradually varied steady flow, when would we get gradually varied? Remember, steady means the discharge is constant throughout the system with time. Gradually varied or non-uniform means that as you move through the system, you're changing the depth of flow, cross-sectional area, and therefore the velocity. Where you get gradually varied steady flow, and we'll be doing examples of this next time, would be in smooth transitions, such as a step, a contraction, an expansion, everything you find in a real channel. When we have gradually varied steady flow, we also typically have hydrostatic pressure distribution. And so basically, when we use this, and let's just ignore the energy losses for now, with an energy balance, you're going from, say, upstream where you have a wide cross-section to downstream where it's contracted. What happens is, when you, just like in a pipe, when you go into a contraction in a pipe, you know the discharge is constant, and because you've contracted the cross-sectional area, the velocity goes up. That had to happen at the expense of pressure. Likewise, if you have changes in the energy terms, so for example, let's say you went into a contraction and therefore you increased the velocity in it. For this to be constant, for energy to be constant, that means there had to be either a reduction in the depth of flow or a reduction in the elevation. So we're going to talk about more on this next class. But the energy equation is still describing the same things in open channels that happen in a pipe. It's complicated by the fact that Froude number and some other things are cropping up that you have to be aware of. So, in rectangular channels, which is very common for what we do in the labs, but it's also common for theoretical developments, the depth of flow is still going to be y. The channel width is going to be b, or some other textbooks will call it w, dimensions of length. The total discharge is capital Q, which has the dimensions of volume per time. And for continuity, we know discharge is velocity times area, which is velocity, and the cross-sectional area is, for a rectangular channel, by. And not uncommonly, what's done is to define what's called the discharge per unit width. Discharge per unit width is the total discharge divided by the width of the channel. And if you look at the continuity equation above, if you divide VBY by B, you get the discharge per unit width being equal to VY. And again, we'll be using this probably more next time. So, the energy equation is built around the Manning equation for open channel flow. And what I mean by that is the friction losses are built into the Manning equation. This is the exact same slide I presented to you before. And on that slide, I said I was going to talk about slope later, and now is later. So, the slope of the Manning equation should always be the slope of the energy grade line. That's what I mentioned to you before. The water surface slope we can call SW, and the bed slope we can call S0. And the figure on this page is the steady uniform flow figure, where those three slopes are parallel. So for steady uniform flow, those three slopes are the same. And again, in design, very often what we will do is put the energy slope in the Manning equation by substituting in the bed slope for design. Ultimately, again, there's a whole course on open channel flow. Ultimately, when you do these analyses, it's a trial and error solution by hand, and there are computer programs that do this for you to calculate the steady, gradually varied, or even rapidly varying flow in these systems. It gets pretty complicated, especially with irregular cross sections. So here's an example just to round out the course. And what we have is a trapezoidal cross section. And in this cross section, we have a base of 8 feet, a depth of flow equal to 6 feet, and then we have side slopes to the trapezoid. And typically, the side slopes are described as so many horizontal units to vertical. So for example, a 3-to-1 side slope means that you have 3 horizontal to 1 vertical. Sometimes we'll call that M, some authors call it Z. And so they'll just say the side slopes, M is equal to 2. In this case, M is equal to 1. And what that basically gives you is this angle, but it also is defining the area in a wetted perimeter. So in this channel, it's lined with gunite. Gunite is just cement that's splattered onto the walls. So we were just doing a culvert lining project on I-89 up in Warner. Bartlett Brook was flowing through these 8-foot diameter corrugated metal pipes, and the bottoms had basically rusted out, and they were under 40 feet of fill. So they're not going to stop the traffic on the interstate to dig up that culvert and replace it. That's a really expensive project. So what they did was line the bottom 1/2 of the pipe with gunite. And so it's basically a concrete that you divert the stream, you reline this culvert, and basically in this culvert that looked like this, the gunite lining looked like this. And so obviously you filled in a bunch of this. That was maybe 3/4 to a foot. So you changed the cross-sectional area, you changed the flow capability, you actually improved the Manning's end, so you really lowered the Manning's end. So after they did this, because of the roughness of corrugated metal, the culvert could actually carry more water than before. But it wasn't, the interstate was never overtopping because you had 40 feet of fill on top of this. The problem was it was too expensive to replace the culvert. So again, the gunite was used in this case as the slip lining. You could use a lot of other materials. And the bed slope of this trapezoidal channel is 0.309. And again, when it's a positive number, that means you're decreasing elevation as you go downhill. So, for this example, we're going to use the Manning equation. And in the Manning equation, that you're given, velocity is equal to some function of everything on the right-hand side. And the question asks for discharge, so if we multiply the Manning equation by cross-sectional area, we get discharge. For gunite, the first thing in the Manning equation, K over N, the table from your book is reproduced here. I just cut off the first 2 lines. For untreated gunite, N is equal to 0.017. If you were using a corrugated metal pipe, the manufacturers would have the roughness coefficient for you. If they don't give you that, you're not going to buy their product because you don't know how to design with it. And you're not going to do your own experiments to figure out Manning's end for someone else's product. For the area of a trapezoid is the area of a rectangle, BY, and then 2 areas of a triangle. And for that triangle, the base is this dimension, and that dimension is my. And the height y is y. So that triangle is 1/2 my squared, and there's two of them. So again, the area of a trapezoid is by, the area of the rectangle, plus 2 my squared. Sorry, there's no 2 in there. 2 times 1/2 is 1. It's just my squared. It is 1/2 over here, and there's 2 of them. Okay, don't get out of this one. So that area is 8 foot times 6 foot. That's the rectangle. M is here, Y is here, and that gives us 84 square feet. The wetted perimeter is the base plus the hypotenuse of 2 triangles. So again, one side of the triangle is y, the other side of the triangle is my, and we want this distance L. That's the wetted perimeter on just that side. So L is equal to the square root of the sum of the squares. M squared, y squared, plus y squared. 1/2 power. And again, there's 2 of those. And so 2, and then you can see you can factor out 1 plus m squared and y squared. So here's the y squared to the 1/2 power, 1 plus m squared. And remember, in this case, m is equal to 1. So this actually turns out to be 24.97 something, something, something. So it just rounds to 25 feet. It's not exactly 25 feet. So there's the wetted perimeter. We have the area of 84 square feet. Wetted perimeter is 25 feet. So that gives us a hydraulic radius of 3.36 feet. And now we have everything to put into the Manning equation. So because all the dimensions were given in BGS, we're working the Manning equation in our system of units. For our system of units, K is 1.49 foot to the 1/3 per second. And again, rarely do you ever see people put dimensions on that. For gunite, the roughness coefficient we looked up is 0.016. The area, we calculated to be 84 square feet. We just calculated the hydraulic radius, and the bed slope was given. So that gives us a discharge of 520 cubic feet per second. So this is a pretty simple example for the Manning equation. If you had the same problem, we could say, given this cross-section question.
Where was K from?
When we first introduced the Manning equation, I introduced K as the conversion factor between meters and feet. 1.486 foot to the 1/3 is equal to 1 meter to the 1/3. Okay? Okay, so in this case, we know the full cross-section from the last problem can handle 576 cubic feet per second. But now, let's say we want to know the depth of flow if there's only 200 CFS flowing in this channel. So in this case, we know it's not going to be the full depth. We want to know the depth of flow of 200 CFS. You solve the problem the exact same way. With the Manning equation. The problem is the depth of flow is built into these hydraulic elements of cross-sectional area and hydraulic radius. So let me just explain explain that on the next slide. So we have, I think red shows up better. Q is equal to K over N, AR to the 2/3, S to the 1/2. And that's equal to K over N, By plus My squared, times By plus My squared, divided by B plus 2y n squared plus 1 to the 2/3 power. That's the 1/2. So the problem is you can bring k, n, and s to the 1/2 over to the left-hand side, but this defies factoring. And so you're left with a trial and error solution. And one way to get at this trial and error solution, again, and if you program this into Excel, you can just use the solver. But one way to do this is you assume y, and then you calculate q from the original way we did this problem. In the original problem, you were told you had a 6-foot depth. But now what you can do is guess at 1, 2, 3, 4, 5 feet of depth, calculate q, and then calculate how far off you are. So, you know, what you would like is to find the depth at which you find 200 CFS. And basically what you would be doing is having a depth of flow. And I'm plotting the independent variable depth of flow on the vertical axis, because typically that's how we measure depth of flow. And so what you're doing is calculating what's called a rating curve. For any given depth of flow, you will have a discharge. And so what you're doing is basically guessing values of depth of flow and calculating a Q. So you're guessing at these blue dots. And if, for example, this one were to be 157 CFS, and this one were to be 221, you know that the 200 CFS is somewhere between those two depths. And you can use either an interpolation scheme, a Newton-Raphson technique, which I don't even know if they still teach you those, but there are a lot of numerical techniques, and that's what the Excel solver uses to actually get at this. So I'm going to leave you with that. Are there any lingering questions on open channel flow? We're going to continue with the subject next class. And I guarantee you will see it in Dr. Malley's wastewater and water treatment system course next semester. You will see all of this.